Perfect. I like the enthusiasm. All right, let's talk about prompting. Before I jump into it, so just a few logistics. Homework 1 is ongoing. I think the correct due date is October 2nd. It's whatever it says on the homework. Don't take the schedule too seriously if it disagrees. Next week, I will start releasing presentation information. You guys can start forming groups in advance of that. 3 to 6 folks is probably good. If you have more for some reason, just come talk to me and we can figure that out. Cool. Any questions about class logistics, things like that? Nope. Awesome. All right, so here's the roadmap. We are really just finishing up prompting today. It's going to be a bunch of sort of techniques, and there's also new ones coming out all the time. Some of these are pretty good subjects for your presentations or even for a project. Then next week, we'll start talking about 2 forms of specialization. One is just kind of the classical fine-tuning for foundation models. How do we train them on a data set to produce the results we want? The other one is a much more special form of kind of specialization / adaptation. It's called alignment. Let's make sure that our models are kind of in tune with what people's communities want from them. After that, we'll start talking about other forms of training, which are super interesting. We'll talk about what's called RLVR. This is reinforcement learning with verifiable rewards. This is the thing that can make models really solve math problems or more challenging reasoning problems. That's one of the most kind of exciting areas of research today. And then we'll start talking about efficiency, so we'll do efficient training and a bunch of other pieces. All right, so here's where we are today. We're going to finish the stuff we started from last time on prompting. We mostly set up terminology and kind of started about how do we do prompts? How do we search for them? How do we get good ones? So we'll finish up on that. And then we'll keep talking about this chain of thought idea, which also very closely relates to reasoning. So chain of thought is going to be a way to encourage our models to actually take a bunch of intermediate steps before they spit out an answer at you. So it's going to be this super popular thing that's actually very simple, but can really dramatically improve performance. And then finally, we'll talk a little bit about, well, how can you actually make sure chain of thought works, what goes into it, and how do we hook up our models with other tools so that they're not stuck doing everything inside the model, but can actually use external resources as well. Cool. Any questions? All right, let's jump in for the first part. So this is kind of where we left off last time. We said that hard prompting is just kind of searching for a good overall prompt. It's not continuous, right? We're just actually tuning all the tokens. And it's hard because of this discrete optimization issue, right? There are no gradients. There's no continuous optimization. There's no simple thing you can do to point yourself in the right direction. OK, and then people have come up with all kinds of nice ways of avoiding this issue. Of course, you can do random search. That's going to be pretty expensive in general. We can do some really simple greedy search. And that's what we talked about last time. So here's a very simple way of simplifying this discrete search problem. Instead of saying we're going to search over the space of all token sequences, which is huge, let's go ahead and kind of reduce that search space. And instead of doing an exhaustive search, let's do greedy. So those are the 2 components that are going to make prompt optimization a bit cheaper. The first thing we're going to do is instead of working at tokens, we're going to work with these sort of phrases, right? So that's what you're seeing of that base instruction over there. Our basic goal is let's get a better instruction, right? This is searching for good prompts that we're going to apply to our problems. And we're going to start with our initial sentence, whatever it is. We're going to break it up into a bunch of phrases, right? So one phrase is your task. One phrase is to classify the tweet, right? Clearly, this is just some prompt instructions for doing sentiment classification for tweets. OK, so what's the point of doing this kind of splitting up the phrases? Well, hopefully, we can actually do a little bit of a cheaper search if we're dealing with phrases instead of individual tokens. OK, how do we get these phrases? We use some standard NLP tools. They can already break up a sentence into relevant phrases. OK, now from there, we don't want to search the space of all the possible phrases either. So what we're going to do is just define some operations. Those operations are the things you're seeing in these arrows. So for example, delete something, swap something, add something. And then from that, you're going to get some candidates for what your instruction could be, for what your prompt should be. Those are all the yellow boxes over there. You're basically seeing the edits that took place, right? We deleted a phrase, we swapped the phrase, and so forth. And how do we know which of these are good? We're actually going to go evaluate them, right? We have some actual data. And we're going to go and see how good does the model do with this prompt on my supervised data set. And we're going to get some scores. And for over there, it seems that the top operation was pretty good. They gave us a high score of 64. Some of these other ones are not as good. We'll keep the best one. And then we'll try this process again. We'll look at some more phrases and so forth. All right, everybody agree with this pretty simple idea? Now, this doesn't produce the optimal prompt, right? It's a very, very, very restricted search space. There's no guarantees that we'll get something good, but it'll give us, with limited compute, some reasonable improvements in prompts. And really, when you think about it, what you're doing when you kind of manually do prompt engineering is not that different from this, right? You're kind of trying out different things, making some small modifications, some tweaks, and seeing what happens score-wise, and then trying again afterwards. OK, so this in itself is kind of an automated form of prompt engineering. So let's talk about automated prompting in general. Not surprisingly, we want to use the same tools that we have access to do this process as well, right? So let's go ahead and try to use LLMs as our own prompt engineers. And it's almost exactly what you think, right? We're going to use an LLM to make suggestions. And then we're going to go ahead and score those suggestions. And then we'll do some procedure with the scores, like take the best one, right? And that's exactly what you're seeing here as well. We're trying to figure out a bunch of possible instructions for a problem. That's what you're seeing in that blue box. It's not so much that we're asking the model to solve a problem. We're asking the model to produce instructions that, when passed into another LLM, would produce good results. So this is some kind of meta thing going on here, right? We're trying to get a model to tell us what are good instructions for a different model to solve a problem. OK, so we get a bunch of candidates from this. As usual, we score the candidates. We throw away the things that are not so good. Maybe we'll take these things that we got as inspiration and pass them back into the initial model to get some more suggestions and so forth. So fairly simple idea. You'll find some cases where the instructions the model gives you are really, really bad. You want to throw those out. So this is automated prompt engineering. Really, models are also kind of doing this in the background all the time. So let's see a quick example. What it came up with in the problem for this paper was, let's work this out step by step to ensure we have the right answer. Right? And you've probably seen similar instructions a bunch of times. We'll see the most popular one kind of later on today. All right, does this sound good for everybody? Go for it.
What do you mean by scoring?
Yeah, so we're going to take the instructions that we got, right? We're going to apply them to a set of problems. Those are the actual tasks happening here. We have some actual ground truth. We're going to see what this second model does when we ask it to actually solve the problem with these instructions. We'll compare the ground truth to get a score. So really what we're saying here is we're swapping the instructions, keeping the data the same, and seeing which instructions are giving you higher scores. Cool. All right, so there's a lot more on this automated prompting subject. The one that I do like, and I think is quite interesting, and maybe we should spend more time thinking about it, is this idea of using an LLM as an optimizer in itself, which is a very strange concept, right? I mean, an LLM is a thing that takes in a sentence and gives you back a different sentence. What do we mean by using it as an optimizer? The kind of thing that we're used to for optimization is an algorithm that actually does a bunch of things, right? So let's see what's possible here. What we're really going to do is we're going to try to replicate the trajectory of an optimizer, right? So for example, when you go train your model, you have some loss function, and you're trying to optimize that function. And then you have a bunch of scores, right? Hopefully, your loss value is going down as the optimization does its work. It generates a sequence of iterates. And those iterates, ideally, have a loss value that goes down. So what you have there in the end is kind of a trajectory, right? You start from wherever you initialize your model to, and then you have this trajectory of weights. And each point in this trajectory, each iterate, hopefully has a lower loss value. Let's see if we can replicate some of this, but interestingly, using an LLM. What we're really going to do here is, rather than say, hey, optimization algorithm, given my current iterate, give me my next one, we're going to use the LLM for that. We're going to say, oh, OK, here are the past few iterates. Can you make the next suggestion for where we should go to? And this is strange, but it kind of makes sense, right? I mean, an LLM is something that can work on language. And in this case, our actual iterates are instructions, right? They're sentences. So it's the right kind of tool to try this kind of thing. All right, so let's take a look. We can basically just run this process in a loop with the LLM as the optimizer. And we'll do few shot, but here few shot means a special thing. It's not kind of generic examples. It's really just the examples you put from your trajectory. Like my previous 3 iterations were this. what should my next iterate be? And we can do this for standard optimization. So for example, we can actually go ahead and train a model by doing this, although that's not really the best use for this. But we can certainly do it for these much more interesting and challenging discrete optimization settings, like prompts as an example. This picture is roughly what's going on here. Unfortunately, it tends to be a little bit challenging to understand. We'll see an example in just a second, which will make a lot more sense. But this is roughly what's happening here, right? We're going to have some meta prompt that tells the LLM that's doing the optimization what it's supposed to be doing. It's telling it, go act as an optimization algorithm. That will generate solutions. We'll have to externally figure out if those solutions make any sense. That's like computing the loss value when we're actually doing optimization. And then we'll get scores from that and go take them back into kind of our overall LLM optimizer. And then finally, when we're done with this process, as in when we've completed our optimization, we'll take the best solutions, for example. OK, at an abstract level, is this OK for everybody?
What do you mean by solution?
So in this case, it's whatever we're optimizing, right? So suppose we're trying to optimize instructions for prompts. The best solutions are the ones that got the highest scores. And these are the iterates at the very end of the optimization process.
Instructional prompts are the solution.
Yeah, it's literally telling the other model what it is it's supposed to be doing. So we're using an LLM to optimize the process of instructions for another LLM to get better. And this makes it especially fun, right? Because you could think of doing this multiple levels. I could do it again for this LLM right here to generate the meta prompt. I could do it again for that one for the meta prompt and so forth. Anyway, think about that. It's kind of fun to think through. OK, let's see an example because it's going to help us understand what's going on here. Here is the complicated meta prompt that we're going to show to the LLM that's acting as an optimizer. It has a lot of pieces, but we can go through it. Now, the parts that you're seeing over here that are colored in orange are these meta instructions. So these are the instructions that we give the LLM that's doing the prompt optimization, telling it what to do to perform this optimization. So these instructions are general. They're not about any particular problem or task. They're for this optimization process. So here's kind of what it says. I have some texts along with their scores. The texts are in order, right, with higher scores coming through. This is basically showing you the previous iterates of the optimization process, right? And it's saying, OK, here's the examples. And then it's showing, hey, for the problem that we're talking about, take these kinds of scores and see what you think you should do. And then finally, generate a new instruction that's different from the old ones and performs better. So this is the full set of details. We're showing this optimization model and telling it, here is the process you should be doing optimization. Here's the old iterates, the old instructions. Here is the problem you're applying them to. You're seeing that over there in purple. And finally, here's the final instruction, which is you should generate a new instruction, and you should make it better. OK, everybody OK, high level with what's going on there?
What's the difference? Thinking auto prompting also we are doing similar thing. We are asking LLM to give a new prompt based on the score. It says that the score
Yes.
is evaluating.
Yes. But notice what we're doing here. We're giving it a lot of freedom to figure out what the trajectory it follows should be. We're telling it, here's the previous iterates. You should figure out something based on the trajectory to do for the next step. Previously, we just said things like, come up with good instructions. Here's some old examples of instructions that were good. Now we're saying, hey, there's some actual optimization process that you should be internally doing to make this work better.
There we weren't passing scores.
We were actually passing scores there too, right?
So that will give it trajectory.
Yeah, and over there, we were just telling it, hey, do a good job. Here we're saying, hey, there is some actual search process you should be doing. There's an actual optimization. That's the only difference. Yeah, that's a good question. All right, so we have these meta instructions that are telling this LLM to act as an optimizer. We're, of course, going to have to tell it we're applying these instructions to a particular problem. They're not generic. The problem in this case is just a basic word problem. So for several years, these word problems were a really good test bed for LLMs because it wasn't totally obvious how to instruct LLMs to solve these things. These things could very easily confuse a model because very often it would just guess some numerical answer without trying to actually solve the problem. And if you think of an LLM as a very basic kind of like generative model, any numerical answer to a question like this is reasonable, right? After all, that's kind of what you'd expect to see coming out when someone asks a question like this. Initially, large language models didn't know they're supposed to actually solve these problems and follow a bunch of steps. And that's why instructions were so important, and that's why this kind of optimization is being applied to word problems. So here's an entire data set of word problems, right? This is the input over here. It has answers. We're telling the model to figure out basically whether its instructions are good enough to produce the right answers internally. And then finally, we're showing it all of these old examples as well. This is the trajectory. Here's the trajectory we were following. We had let's figure it out as one instruction. That wasn't super good. Let's solve the problem. That turned out to be better. And you can guess that sort of more detailed instructions end up being better and better. All right, can anybody guess what is actually going to be a really good instruction here? Go for it.
Let's work through this step by step.
Yeah, so that's the one that we'll come to in just a second. Let's see what actually happened here. So I decided to copy the trajectory from the paper because I do think it's entertaining. OK, solve the following problems using the given information. It's not too bad, 59%, right? Solve the problems by applying the information and doing mathematical operations. That was actually quite a bit better, right? So telling the model that it should be doing mathematical operations is actually helpful, right? Instead of guessing random numbers, it decides, yeah, there's something I should actually do. Let's read the problem carefully and identify the given information. That's even better. And finally, this extremely long and weirdly friendly thing, right? I'm always down for solving a math word problem, blah, 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 turned out to be actually even better. This is one of the fun things about LLMs, right? We've trained them on more or less all of the words in existence. They've picked up all kinds of super interesting biases. So for example, if you're more friendly with them, they actually perform better. Now, we often talk about not treating them as if they're humans, but they do have some very weird human-like properties that are, of course, coming out of their training data. All right, everybody agree with what's going on here? So again, just to summarize what we've been talking about, we said that coming up with good prompts is hard. And then we sort of looked at the specific case of instructions. And these are the instructions you tell a model for what the task is. And then you show it the actual task. And then we decided, OK, we could do all kinds of search procedures, but those are pretty challenging. Let's try to do an optimization procedures where the thing we're optimizing is the actual set of instructions. And then we decided to use an LLM as an optimizer. We told it, hey, go ahead and produce this trajectory for us. We plug the stuff back into the model, ask it for the next instruction that has a better score, and then go ahead and print it out and run the process again and again. And that's what happened here. It created this very detailed instruction for solving word problems that were pretty good. This was step 29, right? So it took us a number of these iterates to get to this point. All right, everybody OK with this? I do actually find it quite fascinating. Here is a very simple one that ended up producing 80%, so quite a good accuracy. Take a deep breath and work on this problem step by step. Now, the step-by-step thing is really the salient thing here. But I do like things like take a deep breath and so forth. All right, everybody OK with this? And again, the thing that I find kind of fascinating, and we should, someone should take it up as a project, what if we are to actually optimize the meta instructions themselves, right? We would have a meta optimizer in that case and so forth. It would be fascinating to see whether we can really get a big performance boost that way as well. OK, so this is pretty much it for kind of thinking through this type of prompt optimization process. There's actually a ton more tools. I haven't even included all the recent ones. We'll spend a bit of time using some higher level tools like DSPy, but that will come a little bit later in the class. For now, we're still kind of talking about lower level automatic prompting optimization. OK, so if we've done a basic form of optimization, we might as well try all of the different basic optimization algorithms out there and see which ones work. So some kind of classic approaches that don't require gradients, and in fact are kind of black box, you could just use classic search, right? So you only really need access to some notion of a neighbor. And of course, you need to do black box evaluation. So hill climbing, right? That's easily applied to prompt optimization. What do I really need to do here? Just define what are close prompts and pick the one that gives me a higher score, and then repeat that process. I could do things like simulated annealing, just basic hill climbing with varying temperature. And then, of course, I can do things like genetic algorithms. Everybody agree with all of these approaches? And all of these are very suitable here. Again, we don't have gradients. We have discrete optimization. Okay, so folks have done these things. This extremely creepy sounding one, prompt breeder, is the genetic algorithm approach for prompt optimization. It basically works in exactly the way you think. Here's what it came up with for a very similar kind of problem. Show all your working. Apparently typos are actually good. You should use the correct mathematical notation and vocabulary, things like that. In general, these days especially, very detailed prompts tend to be a lot better than kind of generic high-level prompts. And sort of the more human-like sounding ones have become a bit less useful over time. A lot of that stuff has kind of been RLHF'd out. Okay, so let's see what this thing looks like. It's a very fancy looking diagram, but it's basically exactly what you'd think. Just like we do in genetic algorithms in general, we have to define two things. One basically is, how do I combine different prompts? If there's something good in this prompt, something good in that prompt, I want to be able to put them together. I do that with higher probability if those are high-scoring prompts. And then finally, I have to define a mutation operator. That's just some small random change that can be produced. Everybody agree? Okay, and then what do I do with these things? I have a set of instructions or prompts. That's my population. I'll perform the standard process, combine high-scoring prompts, perform mutations with some probability, rescore what I got from that. That's the next generation. And then go ahead and repeat this process until I have something really good. Cool. So all of these are very standard search approaches. We can apply them. Nothing is incredibly special here. It's just out-of-the-box use of genetic algorithms, but this time applied to the sentences that make up prompts. All right, any questions so far? Cool. Okay, so we've talked almost entirely about large language models. I think it's time for us to expand at least a tiny bit. Let's talk about prompting other kinds of models, which are not strictly language. So the simplest kind of multimodal model that we'll deal with in this class is going to be a vision language model. And in fact, the simplest vision language foundation model that we'll have is called CLIP. How many of you folks have worked with CLIP? Okay, a bunch of people, which makes sense. For those who are new to it, I'm going to very briefly talk about how CLIP works. CLIP is not itself a generative model. It doesn't have output that's either text or images, but it does work with text and images. And the point of CLIP basically is, given a text input and an image input, you want to be able to say whether those two things are related to each other. Is that text a caption for that image or not? And you want to be able to do this very generically. You don't want to limit yourself to saying, oh, the text can only be one of these classes. The text here can be anything whatsoever. The image can be anything whatsoever. And we want to be able to compare these things. Now, okay, so why would you want to be able to do this? Well, for one, you can basically get kind of open-ended classification, right? So suppose I want to say, hey, here's a new class I've developed. Here's a new possible label. I can put it in my text and say, okay, yeah, is this thing associated with that image or not? Right? So this is actually very, very powerful because you can reuse it whenever. How does it actually work? It's actually the simplest, almost most obvious thing you can do, which is often in ML what works the best. We're going to have two objects that we care about. One is going to be a text encoder. One is going to be an image encoder. You're seeing both of these on the left here. The text is going into the top part. These images are going into the bottom part. Okay, so these encoders, they are not that different from the encoders that we have been talking about, except we haven't shown any image encoders so far. But their job is just to go ahead and turn the objects into representations, specifically into vectors. And then what we can do is to make sure that these vectors, if the image and the text are close, if they correspond to each other, the vectors should be very aligned, literally have high dot product. And if they're not, they should not be aligned. That's pretty much the entirety of what we want to do here. And as a result, we're going to train the model in that exact way. We're going to get a bunch of images with corresponding captions. And then what we'll do here is we'll say, OK, let's go ahead, embed or encode the text, encode the images. When they match, let's make sure their dot product is high. When they don't match, let's make sure that dot product is low. That's actually what you're seeing over here in this big matrix. We're taking the dot product of every one of the image encodings, which is the vector, and text encoding, which is another vector. And we do this for all n of our data points. So you're seeing on this y-axis over here, I1 through in. These are just the embeddings for all the images. And then on top, on the horizontal axis, you're seeing T1 through Tn. Those are all the text vectors. Now, Ti and I, okay, Tj and Ij, these correspond, right? It's the text and image that are paired, but all the other ones do not correspond. Everybody agree? So what we want here is to make sure that this diagonal, which is all the dot products of the matching text and image representations, these should be high. But then all the stuff that's not on the diagonal does not match. It's the caption for the wrong image, so all those dot products should be low. All right, everybody agree with the logic? Okay, so literally all we're going to do is put a loss function on this entire matrix. That loss function will capture exactly what we've talked about. It'll say, hey, make diagonal big, make off diagonal small. And we're going to tune the parameters of the two encoders to ensure we get that. And that's pretty much it for training. This is a process called contrastive training. Contrastive here says matching things should be matching, non-matching things, by contrast, should not be. That's pretty much the entirety of it, so it's extremely simple. In fact, the loss function itself is the most simple one you could come up with for this case. However, this is very easy to scale. You can make this big, and you can get a lot of data. The original model itself was trained on something like 500 million image caption pairs. So this is where you would go, to Flickr, scrape all the images and their captions, use them as your data set, and go ahead and train. And in fact, today we have much larger open source data sets with typically more than 5 billion of these image caption pairs. So it's very easy to train an open clip model. Okay, so that's training on the left here. Let's talk about how we actually go use it, right? So let's suppose that I want to do classification, and I come up with my new set of classes. All I have to do is to encode those classes into a piece of text, a template. That's what you're seeing over here. Here's the kind of classic classes that are coming from CFAR 10, plain, car, dog, blah, blah, blah. We can use anything. I'm going to put them into a photo of that term. Now I have my text. And then I'm going to go ahead and run my text encoder. I'll take the image that I'm trying to classify, compare that image's embedding to all of the text embeddings of the different possible classes, each in their own sentence, and see which one's the biggest. And over in this case, the dog was the biggest, so I can classify it as dog. But again, notice I'm not restricted to that particular set of classes. I could plug in anything there whatsoever. So I can do completely general, open-ended classification here, as opposed to if I trained a model on, let's say, ImageNet, where I'm completely stuck predicting ImageNet classes. Okay, everybody agree with the way clip works and how we can use it? Go for it.
How do we make sure that, let's say, two images are very close to each other, their captions are also bound to be close to each other. So does it give some restrictions on the kind of data that you're using to train clip?
In general, no. We're going to completely ignore that. And you're right, maybe sometimes the caption actually really should be the same for two different images, right? They could contain the same information. We're going to pretend that doesn't happen and ignore it completely. Things will generally work out fine. There are more sophisticated versions that do try to capture the behavior you're talking about. However, the interesting thing is people often create like what are the most challenging cases where things are close. They try to distinguish between those close cases. That'll make the model more powerful. Cool, great question. Other questions about clip? And if you become a machine learning engineer, I promise that you will work with clip at some point, or actually very frequently. Yeah?
So in step 2, can we include some new label we haven't seen before?
Yep, yeah, exactly. So I mean, of course, if the label you're putting in has never played any role in the training data captions, clip will not know what that means. So you won't be able to do anything. But of course, since we're using so many different captions, 500 million, it'll have seen a ton of different things. And therefore, you can be very, very general. All right, awesome questions. Any more questions about clip? Yeah, go for it.
Does that mean that the T1 to T500 million is going over every single possible?
Yes. But of course, we are not really going to go ahead and compare I1 with 500 million text embeddings, right? We're going to form a batch here. The batch will always contain the diagonal element, right, T1 of I1, and then it'll contain the batch size -1 other things, which are images that don't match.
It's going to just pick the one with the highest similarity.
Randomly, actually. The batch will be random, but it always includes the matching guy. You want what's called a positive, and then the remainder of the batch will be negatives in this case. Cool. All right, great questions. Are we ready to see what we can do with clip? Okay, so I've been talking about prompting, so why are we now talking about clip? Well, if you look over here, we're still talking about a piece of text that goes into text encoding. And if you see what's happening, we've kind of fixed the prompt to be this template, a photo of a, and then you plug in what the class name is, right? So this is itself a prompt, and there is nothing stopping us from optimizing this prompt as well, right? For example, a photo of may not really be something that clip is very, very good at understanding. Many of the images that are captioned in the training set don't use the word photo, just as an example. So instead of using these standard templates, we might decide, hey, let's deviate from this. Let's go ahead and optimize our prompt potentially. And this is an example from the actual kind of model information itself. Here's how it works for something more general. Here's 397 different labels for this image, candidates. They're using the a photo of template for everything here. And in this case, it worked, right? It picked out Television Studio out of all the other possibilities. However, we're not always that lucky. And of course, these folks were kind of cherry picking here. They're not going to show you the bad examples. But in general, these are things that can actually struggle quite a bit. You can kind of lock yourself out of performance if you don't optimize these prompts. OK, so what's a way that we might think of how to optimize a prompt for something like clip, where everything is based on descriptions? Well, one thing to note here basically is that there's really two things that we can optimize, right? One is the instructions. In this case, the instructions are just a photo of, right? That's kind of that part of the template. The second thing is the label names themselves, right? There is nothing stopping us from renaming Television Studio to have additional detail there. After all, any additional detail that we put in could get picked up by clip in its inner product, right? You're just giving it more information that goes into its text embedding, and that can be quite useful. So this was actually something that people have introduced a few years ago, and it's quite powerful. Don't use completely static class descriptions. Go ahead and replace them with what are kind of more descriptive features. So instead of saying a photo of a tiger, I might say a photo of an animal that is a tiger, and it has these stripes, it has claws, it has etc. Now, why would I want to do this? Well, maybe just the word tiger itself is not good enough in the text encoder. But if I put in claws, stripes, ... I'll be able to actually get some really good features in my text embedding that actually do correlate well with the image and give me what I want here. Now, one problem, of course, is you might say, hey, I don't have time to annotate all the possible features that are in each class's name. If I have 10,000 classes, like an ImageNet, I don't want to sit down and create, here's all the descriptions for all those classes. Conveniently, it turns out that you can actually just do this with an LLM as well. And in fact, that's one of the general kind of messages for this class. When there's something manual, we can replace it with an LLM, even if we're working on the process of improving LLMs. So here's how you would do this kind of thing. These came out of GPT-3. They're much better now. Instead of using the class name volcano, you replace it with a large cone-shaped mountain, right? And notice that you don't have to just do this once. I can create multiple sets of descriptive features and use all of those. And then I have multiple possibilities, and I'll aggregate them. That's exactly as we were talking about different ways of aggregating prompts last time as well. Everybody OK with this? I think this paper was like a best paper at iClear or something like that. Like incredibly simple idea that just like boosts your performance very, very dramatically. OK, let's talk about a different thing that can happen. And this one I work on, so I am going to use the next 2 minutes completely selfishly to plug some of my students' work. One issue is these things called spurious features in clip. So here's the problem, right? When we're training clip, the model doesn't know anything about what's really happening. It just learns to associate what's in text with what's in pictures. And sometimes pictures often contain the same pair of things and the same text descriptions. But really, there's one particular thing the model's supposed to pick up on, and it accidentally gets the other thing. So let me show you some very quick examples of these. So here's the data set that everybody works with. It's called water birds. The basic idea for water birds is that I have two kinds of birds. bird species that live on land, bird species that live on water. Okay, now I ask my model which one's which. I'm trying to classify these kinds of birds. Now, one problem is that almost all the images of these water species birds, not surprisingly, are somewhere where there's a water in the background. And all of the images of the land birds have backgrounds that are land. Now, that's not shocking, right? It's not impossible to put a water bird over land and vice versa, but typically they're going to be, photos of their natural environments. So not too shockingly, what the model learns is, of course, that it should be looking at a background when it produces this classification. It picks up on this feature that's always there, which is the background. Is it water or land? But that's a spurious feature, right? That's not the actual cause of the species that you are. And as a result, when you go ahead and put a water bird over a land background, the model gets confused. It says, I should be looking at the background. I'll make my prediction based on that, and I'll predict incorrectly as a result. Everybody see what I mean by this? Okay, there's a very famous example from 20 or 30 years ago. The military was training a tank classifier. The story is probably fake, so don't take it too seriously, but everyone tells it, so I will as well. Right, so they had a bunch of images of Soviet tanks, because this was really a long time ago, and NATO tanks. And they trained a model that would classify which one's which. And of course, as it turned out, all of their satellite images of the Soviet tanks came from a cloudy day. The Allied tanks came from a sunny day. So the model learned to distinguish the weather, cloudy versus sunny. And they decided, let's go deploy this in war games and things like that. And predictably, it was a cloudy day, and all the friendly tanks were classified as enemies, and so forth, right? Again, this probably never happened, but these spurious correlations are actually pretty dangerous and kind of worth thinking about. All right, so here's our problem, right? We have an issue with pre-trained models. They're trained on data that contains these spurious correlations, and they have no way of knowing that there is a problem in the first place. Okay, so here's our example that we just talked about. If we have a land bird with a water background, and we do this kind of classification, we pass it in the clip, we have one image embedding, and we have two text embeddings, which are water bird and land bird, it's going to make the wrong prediction because it's picking up on this spurious feature. Okay, so what can we do to deal with this kind of things? Well, interestingly, we can do almost the same trick. We can ask an LLM, hey, what are the spurious features for this problem? And interestingly, if you ask it that information, it will actually know. It may not be able to produce a good prediction, but it will know all about possible spurious correlations. So this is one of these really interesting things about LLMs. Making it do something, it might get it wrong, but if you ask it, what is it that you're supposed to do? What should you take care of? It might tell you the right information. Okay, so these LLMs can tell us what's going on here. And therefore, one thing that we can do is identify a lot of spurious correlations. So for example, background. And then we can modify these embeddings in a way that we can get rid of the influence of background. Okay, I won't spend too much time on this. Again, I'm plugging my student's paper. But essentially what we can do is to ask a different model, hey, what is actually going on? What are the spurious correlations? It will say, oh yeah, here's a bunch of candidate spurious features. You can embed all those candidates as well. And then you can remove those from the embedding that you have. So this is something very interesting that's sometimes called model editing or model steering. I can modify embeddings or representations. I can edit them in such a way that I can get rid of some harmful things. And if you do this, you can fix up your predictions and actually not make these kinds of mistakes. Okay, any questions about this? Go for it.
For preparing the dataset for end of clip model, we had to label things, right?
Well, we didn't label in the traditional set of here's a fixed number of classes, here's each class that's in an image. We just had text captions. And these text captions, it's not like we hired someone to make them. They were being produced as part of some external process. So for example, people write down captions for their images on the internet. You use those guys. Yep.
The foundational model of multimodal model where you can also feed in an image and then tell tell.
Yeah, that's a very good question. I'm intentionally not really talking about the details. There's two possibilities. One is it's just an LLM. And then you literally just ask it the question, hey, I'm classifying water versus land birds. What are some candidate spurious features? And it will give you some textual information. The second is what you're describing. You actually can get an MLLM with vision capabilities. And that thing can say, OK, here's an image. Tell me some possible spurious features. That actually works even better. But as of this paper, which is now 2 years old, we didn't really have good enough ones. Cool. Okay, since we're talking about VLMs, one other thing to be kind of aware of, especially for prompting, is we still have our in-context and few-shot approaches. And they're pretty interesting as well, right? Here's a kind of a fun thing. Let's suppose that you are trying to use a model to figure out, what is a good segmentation of an image. And if you have a vision model, you can do this kind of thing, right? They can output images. They can output anything you'd like. Well, here's an example. We show it one data point, so this is one shot. There's a cat. There's a segmented version of the cat. Then we query it with a new point and look at the output. So you can do things like few-shot learning here as well, even though this is a vision language model. Now, this model is not CLIP, just to be clear. You need a generative model to be able to do this kind of thing. CLIP can only show you embeddings and tell you if they match or don't match. But notice that, again, you can have here, based on the choice that you make of the example image that you show it in few-shot learning, good or bad performance. This one's actually pretty good because it captures the most details of a cat. As you go to the right over here, you have some really bad ones. The image quality is bad, so the model does a very bad job for the example you tell it to actually perform segmentation on. Okay, not really going to go into details of how you really optimize few-shot learning for vision language models, but hopefully everyone at least gets the idea at a high level. Everybody okay with what's being done here? Cool. All right, so with that, let's go ahead and take a break. The next bit is going to be chain of thought. We can take a couple of minutes, and if there's more questions, I'm happy to answer them.
I was talking about this, like when we are generating the then you have to use it, right? Because we don't have.
Oh, what do you mean?
We use the text input and then
So all of the blue lines are the set of classes that we are doing. Yeah, so those are already fixed in advance here. And all of those black things are just going to pass through free and say, hey, what are some descriptive features for this class name? So you're getting everything here for free. The blue ones are the things you want to classify, and then all the things that you're swapping them with are model generated.
okay, but the resolution that is since whenever there is an error, is like
They can. And you'll produce errors as a result of that. It's just that those errors were not substantial enough to really kill you in any way. So this is a very easy task, right? So hallucinations will be very limited in this case. It's not going to come up with anything too crazy.
very generic because we just give any color, like it's supposed to be yellow.
Yeah.
But you can use any color in the image. So arrow is not it's a yellow color bus.
Yeah, it will struggle with things like that. And if you try like really weird, unusual school buses and clip even by default, it won't do a good job there. Yes, that will sometimes make things even worse, is what you're describing. Agree with her.
What's stopping the optimizer to just add more words because the string is unbelievably long?
It will. Yeah, so I agree that can happen. One thing is eventually, if you're taking up so much of the context and there's nothing left to produce actual outputs, the scores will go up, right? So we'll have to shorten something to make the scores go up any further, right? But the verbosity is this a pretty big issue in general. And the other biggest issue too is like, in any kind of automated evaluation, there is another spurious feature with verbosity. So long answers are perceived as better.
Yeah.
And that pushes everything toward producing longer answers. It's a real issue.
What happens if we just add for the score? What happens if we make it really short? We added like a
Yep.
yeah, regulation term, just like it punishes the
Yep.
thing. It's like the context is very, very
Yes, so that's done. Not in the context of this LLM's optimizer, but for eval. So for a couple of years, there was this very famous eval benchmark called Alpaca eval for a bunch of reasons. And for a while, it turned out that like, yeah, indeed, like how long the responses were like extremely influential on model scores. And they did regularize it basically. It's exactly what you're describing. Yeah.
The score of this prompt is also calculated by LLMs or is there another evaluation agent?
So what we do here is we take the instruction, we apply it to a bunch of problems. The problems have ground truth solutions. We compare the model's solutions to second element that takes the instruction and makes a prediction. We can put that prediction to the ground truth, and we average it to get that score.
Well, it's just like benchmark.
Yeah, so this is like having a benchmark or a validation set, right? I need a bunch of those word problems. You saw an example earlier. That's what I get scores from. Now, if you want to have a case where I have no ground truth, yes, you need another model to come and make a guess of whether the answer is correct. And we'll do that kind of thing too. That is basically what's happening. So the modification step here is not like, it's mostly not telling me to focus on things that I really care about. It's mostly telling me to get rid of these other things that I don't care about.
Might work for a complex image, and let's say a small number of features might work for a simple image.
Yes.
So what if we have
Something very similar has been very tourist. Although the usual, it's not sort of like, oh, this image is simple in this case. So you use this. It's a more general case where I'm going to adaptively change how many bits I'm using depending on what I'm doing. Yeah, so it's been called matryoshka embeddings. Matryoshka calls, Russian nesting calls, one sentence inside the other. So you can do that information. I can have a shorter version that compresses all the information, it's all there, or I can have larger versions that sit inside of it. So this has been done. If you're interested in the details, I can send you the Yeah, it's kind of interesting. Actually, there's a student just incidentally, so yeah.
I didn't know they did that the first time. And then once you killed me.
So
I haven't had a second chance. Yes, later in the game, he gives us the best boss in the entire game.
What kind of encoder is used? Is it transform-based?
that's it.
So can you get the attention map of the? I mean, so if I have a text embedding, can I get the attention map from the vision encoder and see?
You can, yeah, so if you're, now for the image encoder, there are different image models that you can use as an encoder. You can use a PIP, which is also attention-based, or you can use a resonance encoder. But sure, you can extract the attention maps, and use it for explainability, interpretability, whatever.
Maybe you can see the text which is given as a prompt, which part of the image is attended.
Yeah, if you're trying to do localization of that kind, that's a very standard thing in like explainable AI. And people do exactly the thing that we're describing. Now, there are arguments that say you cannot actually depend on that kind of thing. Like, there's a ton of different work on like creating heat maps that tell you where the caption is being focused on the image. There's also work that shows that it's not really what's happening. So yes, if you believe in explainable AI, the answer is you can do that. If you don't believe in it, you wouldn't want to do that. But yes, there's a whole lot of those things.
Oh, actually,
Does the exact same thing. It doesn't sense.
Yes. Yes. Let me get slightly more technical here. That won't be much more complicated. What I want to do basically is to identify some subspaces for embedding that contain information that's irrelevant and that causes these various features, right? So I want to say, okay, well, part of the embedding space captures the background, right? I want to get rid of the influence of the background terms. So what I want to do is to project my original embedding onto the subspace orthogonal to this subspace that introduces backside. That's what the projection is. I can also try to boost other components. Like if I think, hey, there's a subspace that gets very relevant information, I really should focus on it and try to boost those components.
Both of those?
No, the inside embedding, just so there's certain components that should be higher. Go ahead and yeah, well, it's more of just, unfortunately, just adding buttons. And you really do an operation there. The one at the bottom is the one that actually has more important. That's a projection onto the orthogonal subspace.
I see. And then
You just take this component, project onto the subspace, and it's all your new component.
but I created
That's your new embedding.
I myself created a function at the end of another week. I would
Very little is really happening. It's literally remove some stuff, makes one of them separate, and perform the original operation with the new version of the embedding. Yeah, that's the selection last step.
Just like predict this strength, right? It needs something else to
You can put a single word if you want, right? Like we can get rid of a photo of it and just have the object.
But you have to have code, right? You can't just like say right tweet it.
No.
Yes, there's no emission generation component here. This thing is a one-way operation that based on an image using. There's nothing else you can do here.
Also, this here, this is an example.
No, they ran their procedure to reduce that.
This is also
The algorithm reduces a bunch of candidates by picking two things, right? Operations and whatever new information. Very, very simple. I mean, the difference is going to be in like when you tell it to create different candidates, what are you telling it? Pretty much the only thing that's happening.
It should have more sophisticated like scoring technique too. I'm not sure.
Not really. It's basically the same thing. Yeah. Yes, you can change the metric. Yeah.
Okay, thank you.
Yeah, all of these are very, very similar.
Text encodings like the descriptions or like a cousin with more descriptive sets of characters, let's say.
It's going to increase the text.
You actually, yes, those text is longer. And actually slightly worse, I have to run the model multiple times because I might use all of these guys, right? Yeah, use different instructions. So yeah, I pay a little bit of cost in terms of like compute. But this model is actually very cheap, right? This isn't some giant transformer that takes me a long time, right? Very small encoder, just get the embedding, compute it like that. So we never really hear too much about inference down cost or flow. Yep. All right, folks, thank you for all the great questions. Let's keep going. Let's start talking about chain of thought. So we'll talk about the basic idea. As usual, we'll split chain of thought prompting into two. So 0 shot, we give no additional examples, and few shot, where there actually are additional examples. Then we're going to talk about the usual thing, how do we choose examples? And then finally, we'll go through and discuss some more advanced forms of chain of thought, which actually kind of lead us into reasoning overall. We'll talk more about that next week. Okay, so here's the basic idea for chain of thought. If I want to do some complex operation for my model, let's give it some help. And here's the really basic example that we're going to show. Here is standard one-shot prompting on the left. I have this word problem. Again, this is the basic thing that in general we're using to kind of figure out how good models are. We show it one example of a worked out word problem. That's Roger has 5 tennis balls, blah, blah, blah. We give it the correct answer, right? So the answer is 11. And then we ask our question and tell it to produce an answer. Now, the thing that the model is going to do is it's going to spend some time thinking through, hey, let me produce an answer that looks very similar, format-wise, to what's happening in the example. And that means it's going to say the answer is something, right? And that's exactly what the model is doing over here as well. The problem is, this is a math problem that involves a couple of steps with intermediate operations, right? And right now, the model doesn't have any room to perform those operations, store their answers, do anything with them. And because it has no room to do any of those things, the best it can do is to guess a number. Maybe a number that roughly looks like the number from the example. So it guessed 27, which is wrong, but it couldn't really do anything else, right? Keep in mind, these models do not have some scratch paper on the side that they can do some work on. All they can do is to produce tokens, and all they can do internally is do whatever operations they can approximate during their layers. So they don't really have a bunch of state and memory that they can do stuff with. So this is why we're going to do chain of thought. We're basically going to give it room to do these things and give it the ability to actually perform small, simple operations and then put them together. And how do we encourage the model to do that? Well, in this case, it's actually very simple. We just had a worked out solution for our example. So that's this blue part that you're seeing here. Instead of just saying the answer is 11, you're now showing a full solution that goes step by step. And that says, okay, well, you start with 5, 2 times 3 is 6, add 5 to 6, blah, 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 right? And now as a result, the model is encouraged to do a similar set of operations as well. So it has two things that are going on now. One is literally it has room to produce all this extra work, actually store those answers, right, as output tokens. But second, it's also going to be encouraged to do small operations that can actually perform. And therefore, it ends up getting this answer right. And it is impressive that we changed almost nothing, right? We just provided some more steps. And as a result, it actually worked. And this is not a toy example that was cherry-picked. It really does boost performance on these kinds of things very, very dramatically. OK, everybody get the idea? Cool. All right, so what are the applications here? It's exactly all of the cases where you do have intermediate steps that you have to do. So we just saw examples of math problems. Not the only place. In general, reasoning of any sort, not just for math and not just for academic things, is actually quite useful. And finally, if you want to do any kind of symbolic processing or reasoning, same deal, right? And here's a bunch of examples that came from the original paper. You're seeing, kind of for each class, basic math word problems, things where you do have to think about things, right? Would a pear sink in water? That's a trivia question in one way. Maybe you just know the answer off the top of your head. Maybe the model hasn't memorized. If we're lucky, that'd be good. But really, the way you solve this kind of problem is by thinking through what's involved to answer it, right? What does it mean to sink in water? Well, you have to be more dense than water. How do I know if something will therefore sink in water? Well, I have to figure out if it's more dense, and if so, it will, right? Is a pear more dense than water? Yes, right? So this is very basic forms of reasoning. But again, if you make your model just guess an output, it will struggle unless it's memorized a straightforward, direct answer. And same thing with anything that involves these kinds of simple symbolic calculations, like take the last letter and so forth. And of course, LLMs are very notoriously bad at a lot of these sort of formulaic things. You've probably seen many of these examples. Count the number of R's, or the number of appearances of the letter R in a word, and so forth. All right, everybody see these applications and agree with them? Now, chain of thought is not guaranteed to solve all of these kinds of problems correctly. You still need to be able to do a bunch of things. And one general issue is the longer the number of steps, the easier it is for the model to forget something, to make a mistake somewhere, right? So chain of thought isn't like a panacea that's going to solve everything, but it's going to give us a chance at a lot of these problems. And really, this is sort of the first thing where people genuinely believe that you can make models perform these types of problems and these kind of calculations. And it's led to kind of all of the reasoning-based models that exist today. All right, so one way that we kind of said we can do chain of thought is by showing worked out examples that are step-by-step. But perhaps we don't have any such examples. In that case, we'll have to do something different. So zero-shot chain of thought comes down to the thing that we talked about. Make sure you give instructions that tell the model to actually do this kind of step-by-step intermediate thinking. So in this case, we're going to do the famous let's think step-by-step. That's kind of the most popular zero-shot chain of thought instruction. Now, can we do better? The answer is yes, right? We had all of that prompt optimization to create better instructions that we can use here. OK, now, if we want to make sure that we can get the right kind of answer, we also have to do formatting stuff. And then we've seen these things before, too. So therefore, the answer, Arabic numerals, right, if I want to be able to extract a numerical answer from it. So this is kind of like all the possible cases that we have here. On the left, you're seeing without chain of thought, either few-shot or zero-shot. On the right, we're looking at few-shot chain of thought, which is go ahead and include all of the detailed solution steps for your examples. Or zero-shot chain of thought, which is just, OK, add an instruction to it to tell it you should be doing this. Any questions? Everybody good? Cool. OK, now one thing that's less fun these days is that pretty much every model in its system prompt knows that for some problems it's supposed to do this. So there's no real value in you manually adding let's think step-by-step to your prompts currently. That's already sitting there in the background. There's nothing interesting going on that you can actually increase its abilities. However, if you're showing the model some very specialized kind of problem, where the actual sets of things and operations you'll do are special, you may want to create something more detailed. Let's think step-by-step in the following way. That can actually still be helpful. Cool, so let's see some examples over here. We still have to choose the examples that we're going to put in the prompt for few-shot. There's a bunch of different ways of doing this, just like we saw last time. So for example, complexity-based is an interesting one. More complex is better than simpler. In general, skipping steps is hard. models don't have the same intuition that you have. You want to make sure that you actually give them a ton of detail, for example. Okay, so let's say that we're going to include most steps. And then finally, we can do all the tricks that we talked about last time as well. Instead of running this once and taking the answer, we can run it multiple times and run something like majority vote over the outputs. So here's kind of what's going on. We're trying to pick out of all these different types of chain of thought examples, right? So over here, putting in more steps, 9 total steps, and being more detailed, turns out to be better than kind of skipping any of these steps. And then finally, I can do a ton of different generations. Here's 5 of them, right? I can pick the majority voting, which is the one that's most popular. But I can also weight that majority vote to kind of more heavily focus on the ones that are more complex. So that's what these guys do. They say, OK, for the complex reasoning chains, the ones that have more than 3 steps, I should just keep those. Those ones more often said 200 is the right answer, so pick 200. OK, a bunch of simple tricks. These are actually still being used all the time. The new terminology, as I mentioned, I think last time or maybe even last week, is called test time scaling. Increase the number of inference calls you make and try to pick out the best ones, either by having external access to some tool that tells you this is indeed the right answer, or potentially, just like here, run a majority vote, possibly weighted to do something. All right, everybody OK with this? There's no guarantee, by the way. If you actually end up getting kind of chain of thought examples that are so detailed that each step barely does anything, you'll also confuse the model. So there's some kind of sweet spot that you still have to target. OK, so this is chain of thought. We can get a little bit more general than chain of thought. Now, when we do reasoning ourselves, right, what you do is not, let me think of a solution to my problem, and then tomorrow, delete the whole solution, think of a totally new solution, a whole new chain of reasoning, and then the next day try it again, right? Well, at least typically that's not what happens. It's pretty difficult to fully forget everything you tried. So we don't really sample a bunch of chains of reasoning and do majority vote at the end or anything like that. We do something a bit more iterative than that. Typically, we'll have some kind of tree, right? We're thinking of how to solve a problem. There's 2 approaches that we could use. For the first approach, there's 3 things we can try. For the second approach, there's 2 things we can try. Of each of those things we try, there's some steps that we have to follow and so forth. Right, so we have this big tree that branches out, and then we get to the end for each of these possible candidate ways of going down the tree, and then we pick one of those as the correct way to solve the problem. That's a very, very rough approximation of the thinking process that we have internally. Well, not surprisingly, people have tried a very similar thing with chain of thought, which is over here. It's called tree of thoughts. And it's exactly the process that we've talked about. Instead of saying, OK, go ahead and find a solution step by step, you say, well, here's the 3 candidate first steps that we could have. And from there, I split up, the first one, here's the next step. For the middle possibility, here's 3 possible next steps. It's exactly that tree that we're seeing over there. Now, of course, in the end, we'll have to get down to the leaves and pick out one of those chains, and that will be our final answer. But this is a much more reasonable way to kind of approximate reasoning than what we're seeing over here. And these are the things that we just talked about, right? We could have direct output from the input. That is no chain of thought at all. We said this will break for a lot of problems. Here's the most basic chain of thought. I just have a bunch of fixed steps that I follow. And then finally, this thing called self-consistency is just majority vote. I run many chains. I pick the majority among the outputs, maybe weighted based on complexity or something else. All right, everybody agree with all the possibilities for chain of thought? Notice as well that there's an efficiency angle, right? If I just do self-consistency, and if I don't do majority vote, but I have some verifier that says, OK, the answer you got is right or wrong, then if my reasoning chain includes something pretty rare, I'll have to generate thousands of those chains before I get to the right answer. If I start using my tree over here, I may not have to sample down the same path so many times. OK, so let's get a little bit into this tree of thought, which is actually quite nice. So here's some very basic notation. I'm going to consider these intermediate steps, which are themselves just token sequences. I'm going to call them Z. So the process is going to be start with input X. Then I have this intermediate thought, which is just a step, Z1. From Z1, I can go to Z2. I'll go up to Zn. And then finally, I'll have my output Y. So a full chain would be X to Z1 to Z2 to Zn to Y. Okay, so let's go ahead and look at what the other methods are based on using this notation. Right, so for vanilla chain of thought, what I'm going to do is for each generated zi, put it into the context, in other words, condition on it, and then sample my next thought. Right, that's just what a language model does. So zi is sampled from the language model. That's the theta that you're seeing here. Its distribution conditioned on x and all the previous thoughts I've generated. Cool. Then finally for y, after I've completed all my intermediate thoughts, I've computed zn, I sample my output y as well, also from the language model. Right, and then self-consistency / majority vote is just running that process all the way to y repeatedly. And then I take all the candidate y's and pick one out by whatever means I want to use. Okay, so instead, let's go ahead and be a little more clever. Let's create a current state which has the input and some number of these z's. It could be up to zi or zn. We'll generate multiple candidates for the next state. And by doing this, I'll be able to draw one of these trees. And then I can run whatever approach I want to run on this thing. Right? So I can run breadth first search. Or I can run depth first search if I want to. Or I can run any other approach if I want to have heuristics play a role. I can run A star and so forth. All right, so here's kind of the key aspects. How do you kind of figure out how big these thoughts should be? We said, hey, more detailed, more complex is better. Unfortunately, that does mean that the number of states gets very large. So there's some efficiency trade-off when it comes to searching the tree. You have to be careful with this part. The next part is, how do I obtain the next sample, right? So how do I get all of these candidates? One thing I want to avoid is duplicating things too much. And then finally, this is kind of bringing in this heuristic aspect. How close are we to a solution? How do I know I'm in a good state and I should keep at this state or generate more candidates for it? So again, here there's a whole bunch of different ways of doing a solution. One aspect basically is just go ahead and use another language model or the language model itself to guess how close we are. Okay, and the search that these folks did was just basic BFS or DFS, or we can do all the more advanced things. Let me show you guys a quick example, which is easier to kind of go through. Here's a really simple kind of game that you can play. It's called the Game of 24. It's math reasoning, and it's still very elementary, but it's a bit more complex than those kinds of math word problems that we've been seeing so far. The basic idea is I'm going to start with 4 numbers. It can be whatever. The input 4 numbers in this particular example are 4, 9, 10, and 13. But again, they could be different. These are not the only ones. I'm going to place mathematical operations. So again, plus, minus, multiply, divide. And I can put in parentheses. And I have to do that with these numbers until I produce 24. All right, so over here, the way you could get to 24 is something like the following. Put a minus between 10 and 4. Do that operation, so put parentheses. Put a minus between 13 and 9, right? And go ahead and put parentheses between these. You get 6 times 4, which is 24. Okay, now notice that this is not a very easy thing for a language model to do, right? How do you solve this problem? Get out a piece of paper and try a bunch of things, right? Start putting some operations in and see what happens. And what you really want to do here is not, hey, let me randomly guess some operations and see if the answer is right and start over, right? I'll do an intermediate thing. So for example, I could start by saying, oh, let me put a plus between 10 and 4, and then try a bunch of things from that point. And of course, I'll quickly realize, well, 10 plus 4 is too big. Nothing else I do makes sense. Okay, then I'll start over. I'll say put a minus between 10 and 4. What can we do from that point? Generate some next candidates and so forth. So the way you would solve this problem really is by doing a search over a tree. Let's let the model do exactly the same thing. And that's what's going on here, right? So we propose a prompt. We'll have some thought generation. Here's some candidate thoughts, right? Go ahead and do 4 plus 9 or 10 minus 4, right? Let's see if we think this leads somewhere good. Very quickly, the model will sometimes tell you, hey, I think that's impossible. This state is probably a dead end. It's not going to reach the answer. And just repeat this process and explore the tree. And that's what you're seeing on the left over here, right? We went down this middle path. We also explored the right path, but we decided, hey, 13 is too big. From the middle path, we decided against some other options. These guys scored very low, so we stopped exploring that part of the tree. And then finally, we got to the right answer. Okay, so it's a simple toy, a little bit contrived type of problem, but you can see the power of this type of approach. So really, and this is increasingly true for reasoning models, it's not really just about language. Increasingly, we're doing search with a very flexible interface. And that's what this is, right? I could have really solved this problem using the same search procedure if I had earlier on formalized it, right, into something that I could run a search process over. Here, I can do it all through prompting. And that's really so much of what language models do now. All right, everybody okay with this? Anybody confused? Could you implement this? And by implement, I mean literally just write the prompts, right? Because nothing else is really happening here. Cool. All right, let me jump ahead. This is going to be our break, but let's spend the last 5 minutes of class talking a little bit about what we can do to make chain of thought better, and then finally, using external tools. Okay, so there's some really interesting work that was proposed recently that tried to understand, well, first, what makes chain of thought happen? There's no guarantee that the model will actually react the way you want it to. And second, what helps? Okay, so do all models have this chain of thought behavior? So the answer actually, interestingly, is no. If your model is too small, then you actually cannot really do anything. It will not do step-by-step reasoning, no matter what you tell it. You can show it plenty of examples, it won't be able to do it. Now, later, as in next week, we're going to see how to use RL to kind of get around this issue. But I think this is a very nice plot showing you what's happening here. The x-axis are model sizes from less than 1 billion to 100 billion parameters. Again, if you recall, even a model like GPT-3 was already in the hundreds of billions of parameters. And the interesting thing here is that if you're seeing that black curve, basically, right, you're seeing not much improvement, right? Now chain of thought doesn't do too much for you. The bigger model does something better. The blue is with chain of thought, but at least initially it does nothing, right? No improvement whatsoever for these smaller size models, and then suddenly huge improvement for the larger models. So just because you do chain of thought doesn't mean that it's guaranteed to work. Sometimes it does nothing at all, and some of that has to do with model sizing. These larger models have the capacity to handle chain of thought. The smaller models, even if you tell them to do this, will not really do anything for you. However, like I said, soon we're going to use RL to force our models to actually do reasoning. And by doing this, we're going to be able to take this curve and change it very dramatically. We can get 1 billion parameter models that can do chain of thought. Of course, there will be some other limitations because there's no free lunch entirely, but we'll be able to undo some of these effects. Okay, so this says basically chain of thought doesn't really help until we get past 10 billion parameters. This is mostly on math problems. When this behavior shows up depends on the actual domain that you're using. Now, here's the thing that is completely fascinating. You might ask, well, does it really matter if my examples I'm showing for chain of thought are actually correct or not correct? Surprisingly, the answer is no, it's not as important as you think. So when you show the model an example for chain of thought, it's not really looking inside that example at figuring out exactly what the operations are and how to reproduce them exactly. It's just learning in a vague way roughly what's supposed to happen, but it's not reproducing the calculation itself. So in fact, you can replace some of your examples with wrong examples altogether, and it doesn't really very dramatically change the performance of your model. Really, you're telling it the flavor of how to approach a problem, not the exact correct details, and that turns out to be good enough. Yeah?
Have you ever been able to amend processes that have been used in prompting to try and show like a different process for doing it with the chain of thought, effectively saying like, oh, you're doing this wrong, here, let me show you how it's done?
Yes, but in very simplistic ways.
Okay.
Well, the problem is, yeah, connecting what the model is really doing to these high-level operations is itself a huge lift. You have to get into a bunch of circuit analysis stuff to figure that out. And we'll talk more about that later. But what you're suggesting is very non-trivial. Cool. So strangely enough, correctness is not that important. Scale was important. Let's very briefly see in our last minute some other examples of what matters. We do want these relevant steps, and we want the steps to follow each other, but they don't have to be right, amazingly enough. Okay, additionally, you might think, hey, I really need some human signal, right, to be able for the model to figure out what it's supposed to do. Not necessarily. Very interestingly, if you do get a model to output one good chain of thought example, it can reuse that again and again. So again, this is another case where somewhere inside these models, there is the information that they need to be able to solve problems. You just have to find a way of exposing it and making the model rely on it. So we'll see this happening again and again and again. These huge models know a lot and know how to do a lot. They just don't necessarily do it unless you find the right way to kind of poke it to do that. Okay, one more example. Pre-training is also pretty interesting. It turns out that pre-training is not itself the most critical thing for chain of thought. I'll talk more about this next time, but it's not like, in pre-training it saw let's think step by step a million times and therefore learn that it's supposed to do it for that particular instruction. Let's stop here. We'll continue this next week. And again, remember that the homework is also going to be due next week. Office hours this afternoon if anyone has questions. See you all later.